now we're drawing.
One-dimensional kinematics.
This is Chewy running on a flat horizontal strip for 5.791 meters to the left. Friction and air resistance are negligible for the sake of this experiment. We insert this clip into Tracker in order to analyze Chewy's relationship between position and time while running. Here, the axis is labeled with the total horizontal displacement to the left, and we have used the point mass function to track his position over the duration of his run.
From the point mass tracking, the software generated a position versus time graph as shown for the 1.6-second interval. Using the equation change of x equals vt, we know that the slope of this graph is reflective of the velocity of Chewy. Since the position versus time graph is linear, the slope is constant and the acceleration is zero. Here is the velocity versus time graph for Chewy's horizontal run. The equation vf equals vi plus at can be rearranged to show that acceleration equals change in velocity over time. So acceleration equals the slope of the velocity versus time graph, which is zero in Chewy's case.
Next, we wanted to look at the kinematics involved in vertical motion, so we dropped a tennis ball initially at rest into Chewy's mouth. The clip and Tracker again used point mass analysis to track the ball's motion from my hand to his mouth over the vertical distance of 2.29 meters and created another position versus time graph using the y displacement of the ball. The same conceptual patterns are true for the slopes of the position versus time and velocity versus time graphs, but since the ball is accelerating due to gravity, the velocity is not constant and results in a parabolic position versus time graph.
Comparing the parabolic position versus time and linear position versus time, the parabolic shape has a wider range of instantaneous velocities, meaning at each position the velocity of the point or Chewy or the ball is changing, indicating some non-zero acceleration. This can be represented by the third row of position velocity acceleration graphs. For an object with zero acceleration but constant non-zero velocity, the position will be increasing linearly, which is why delta x equals vi times t is true, and Chewy's run was a straight line.
Also, if we had chosen to track Chewy or the ball's velocity versus time, the area under the curve would have represented displacement. Similarly, the area under the curve of acceleration versus time equals the change in velocity.
To understand the data mathematically, we use these three equations, all designated for one-dimensional kinematics, to solve for unknowns in each of our experiments. The first shows that v final equals v initial plus at. Since we know that the ball is acting without external forces, acceleration equals gravity, and t is told by the graph. And since we dropped it from rest, the equation can be reduced to v final equals gravity times time. And after solving, we know the velocity of the ball at the bottom of the drop is approximately 7.0226 meters per second downward. Had we dropped the ball with some initial velocity downward, t would decrease and v final would approach a certain free fall velocity. Also, had we thrown the ball up so it made a parabolic-like path, the instantaneous velocity at the top is equal to zero, but has the same displacement because it passes through the start and would have a higher v final.
You don't care. No, I don't.
The second equation we also use for the ball trial is vf squared equals vi squared plus 2a delta y. Again, it dropped from rest and a equals g, so vf squared equals the square root of 2g delta y. This value is slightly different from vf because delta y is considered instead of time. If delta y increases, vf increases with a square root proportion. If we had thrown the ball up, the change in y would still be 2.29 meters because the ball had to come back through its original position, but v initial would be some non-zero value because it has fallen.
The last equation we used for the horizontal jog, change in x equals vit plus 1/2 at squared, can be reduced because in this trial there was no acceleration in the horizontal direction, making it change of x equals vit. Using the known distance Chewy traveled since he did not change directions, change of x is 5.791 meters, and t from the graph is 1.6 seconds. So vi equals 3.62 meters per second. Since there was no acceleration, vi equals vf. If there had been positive acceleration, change in x would increase and vf would differ from vi. These equations can all be used in either the horizontal or vertical directions as long as proper direction is established.